X-ray diffraction has many different applications. An important application of X-ray diffraction is phase analysis. Now, phase analysis is quite different from elemental chemical analysis. Say for example, if we have a compound say AU CU3 or CUZN or anything, this is a single phase, although made up of two components, one is gold, the other is copper. Similarly, when we talk about CUZN, it is a single phase made up of the elements copper and zinc. Normal chemical analysis constitutes the technique to find out how much of each element is present in a particular phase or in a particular element. But when we talk about the phase analysis, it is not elemental chemical analysis we talk about the individual phases. Now, it so happens that any phase made up of an element or a compound of several elements, if we have a phase made up of a single element or a compound of many different elements, then X-ray diffraction from that phase will yield a unique diffraction pattern. So, what we mean by a diffraction pattern? The diffraction pattern taken from a particular phase will have a number of diffraction lines at definite theta values. Say for example, this is the diffraction pattern taken from a particular phase. Now, the diffraction pattern consists of a number of lines 1 1, 2 2, 3 3, 4 4, 5 5, etc. And these are positioned at particular theta values, and these are positioned at particular theta values. Over and above that, these diffraction lines have different relative intensity values. Say for example, the line 1 1 has a very strong intensity, like 5 5 4, 5 5 also has a strong intensity. Line 2 2 has a somewhat less intensity, 3 3 and 4 4 have even less intensity. Now, when we talk about a diffraction pattern, we talk about two things at the same time: the location of the lines at particular theta values and their relative intensity. So, relative intensity of the diffraction lines is also very, very important. Say if I 0 is the intensity of the strongest line in the pattern, then the relative intensity of a line can be found out by taking the ratio I by I 0, where I stands for the intensity of a particular line. So, when we talk about the powder diffraction pattern from a phase, it may be an element, it may be a compound, then both the things are very important to note. So, we must find out where the lines, diffraction lines form at what theta values and what are the relative intensities of the lines. Now, this diffraction pattern is very unique for a particular phase, whether an element or a compound. Say for example, we have got this diffraction pattern from an element or a phase A. Now, if we find out the diffraction pattern for another phase or element B, then these two will be quite different. In fact, just as by recording the fingerprint from two different persons, they can be distinguished because each person has a definite type of fingerprint which is unique to that person alone. Similarly, the diffraction patterns taken from two elements A and B or two phases A and B are also very unique to the corresponding materials. The diffraction pattern from two different elements or two different phases cannot be the same. And when we talk about the pattern, we must remember two things: the locations of the lines on the pattern at certain theta values as well as their relative intensity of the lines. So, these two together will constitute what is known as the diffraction pattern. So, no two elements or compounds or phases can have the same diffraction pattern. So, any element, compound or phase can be recognized by its corresponding diffraction pattern. So, this is a very important thing that we have found out, that every material, every element, compound or phase will have its unique diffraction pattern characterized by the lines at some definite theta values and their relative intensities. So, this gives us a method of identifying an element or a compound or a phase. So, as we will see that this phase analysis can be done in a qualitative manner and also in a quantitative manner. So, in this lecture I will discuss about qualitative phase analysis by X-ray diffraction. Now, this method evolved over a period of years, and it owes a lot to the effort of Hanawalt. So, Hanawalt and his associates, they built up a collection of X-ray powder diffraction data from patterns of known substances. Now, these were later printed as a set of 3" by 5" cards under the auspices of the American Society of Testing Materials. Now, an STM diffraction data card is shown here. These cards, known as the STM diffraction data cards, they constitute what is known as the powder diffraction file or PDF, the powder diffraction file or PDF. So, the powder diffraction file will consist of data from a large number of substances whose diffraction patterns were taken by researchers all over the world. Now, if we look at a particular STM diffraction data card in the PDF, we will find the following characteristics, following features. There is a 5-digit number for each card, then the D values of the 3 most strong lines in the XRD patterns of the substance along with their relative intensities are present. Say for example, in this case the 3 strongest lines have got D values of 2.28 angstrom, 1.50 angstrom, 1.35 angstrom, and the corresponding relative intensities are 100, 35 and 35. In addition, we also have the D value, the highest D value that we can obtain from this material. So, this material shows the highest D value of 2.6, which is recorded here, and the corresponding relative intensity is also shown here. Now, the method that has been used for obtaining the diffraction pattern of the material under consideration, which is MO2C in this particular case, those are shown over here. This is followed by the various crystallographic, optical and chemical data of this material here. Okay. Now, finally, the values of D, the interplanar distances and relative intensities I by I0 for all the observed diffraction lines in the pattern are shown on the right hand side. So, in this column the D values are recorded, and here in this column the relative intensities, same over here and here. So, this card represents a powder pattern completely. So, now if we have say hundreds and thousands of materials whose X-ray diffraction patterns were taken by various researchers all over the world, we can produce such a card for each different element, compound or phase and put them for our future reference. Now, what kind of method we can use for qualitatively determining the phase or determine the identity of a unknown phase, unknown elemental compound? We just take the diffraction pattern from the unknown material and try to compare the data for that particular material with the data provided in the many thousands of ASTM diffraction data cards. And if we find that there is a match, complete match of the diffraction pattern of the unknown material with that of the data in one of these cards, then the identity of the unknown material becomes known. So, this is basically the method of qualitative phase analysis. Now, you see, when we have a large number of cards, each card giving the diffraction data for one particular element or compound or phase, then locating a card in the powder diffraction file may become quite time consuming and laborious. So, what is to be done? To begin with, these cards initially were placed in a drawer in a manner similar to the arrangement of the catalog cards earlier used in a library. With the increase in the number of cards in the powder diffraction file, the identification process became cumbersome. To overcome this problem, two search manuals in the form of books were prepared, which are to be used with the powder diffraction file, and these two books have the following information. Now, one manual has an alphabetic index of each substance by name. This name is followed by the chemical formula of the substance, the D values of the three strongest lines, the relative intensities of the three strongest lines, and the serial number of the card in the powder diffraction file. The other manual has a numerical index. It gives first the D spacings of the three strongest lines, the relative intensities of the three strongest lines, the chemical formula, the name of the substance, and the serial number of the card in the powder diffraction file. So, using these two manuals, it becomes much easier to locate the desired card in the system of thousands of cards in the PDF. Now, the PDF is revised from time to time. It needs continued revision and updating, because new data on new substances become available from time to time. Now, there has been a committee called the Joint Committee on Powder Diffraction Standards, in short JCPDS, of the International Center for Diffraction Data, ICDD. They started developing a large computer base of all such diffraction information from many substances. So, in 1962, the information on D spacings, relative intensities of diffraction lines, the formulae and PDF numbers were first keyboarded for a computer readable database. Later, an online search service for computer based search and matching activities using the above database was started by JCPDS. Increased use of the computer based PDF led to the discontinuation of the production of cards from 1987 onwards. The only hard copies that were published were in the form of books. The modern automated powder diffractometers, which was developed by many manufacturers, they use the computer readable powder diffraction file database for phase identification. They also supply the necessary software for this purpose. Now, I will show the application of the Hanawalt method. So, first you have to prepare the XRD pattern of the unknown sample. Either you can make it by the Debye camera or using a diffractometer. And we use a convenient X radiation, a convenient characteristic X radiation, which will produce an adequate number of lines on the pattern with minimum fluorescence, that means minimum background radiation. Now, the powder diffraction lines recorded in this manner were mostly using the molybdenum K alpha characteristic radiation. So, most of the diffraction patterns of many substances were prepared by ASTM, and they used a Debye camera and a molybdenum K alpha characteristic radiation. The relative intensities of the diffraction lines in a pattern may change when the pattern is taken using different characteristic radiations. So, this is a very important fact to know. Thus, the XRD pattern of a substance obtained with copper K alpha radiation may not be directly comparable with the pattern of the same substance using molybdenum K alpha radiation. So, the necessary factors for the conversion of intensities from copper K alpha to a molybdenum K alpha basis, these are all given in an introductory card in the ASTM file. So, this is a very important thing to remember. Now, once a pattern is obtained, the D values of all the lines present in the pattern are tabulated in this manner along with the relative intensity of each and every line. Say for example, we have got a powder pattern taken with the help of a Debye camera as shown in the diagram. Now, once the pattern is taken, as I already said, the interplanar spacings D's for each and every line pair are determined. And what about the relative intensities? Normally, the relative intensities are determined for the purpose of qualitative phase analysis by eye estimation. Again, ASTM has suggested that the strongest line in the pattern should be given the tag very strong, VVS. So, its relative intensity is taken as 100. Then comes the very strong or Vs lines having relative intensity around 90. Then comes the strong lines with relative intensity between 70 to 80. Then comes the medium strong Ms with relative intensity lying between say 50 to 60. Then comes the weak lines with relative intensities 30 to 40, the faint or F lines with relative intensity around 20, and very faint or VF lines with relative intensity of around 10. So, this type of a scale we normally use to estimate the relative intensities of the different lines in the pattern by eye estimation, as has been done in this particular case. Now, say for example, we have taken the Debye diffraction pattern from an unknown sample having an effective camera radius or camera diameter of say 8.41 centimeter and copper K alpha radiation having a wavelength of 1.542 angstrom. The diffraction pattern is shown on the screen, and from each and every line pair we could find out their HKL values in the usual manner and their D's together with the relative intensities. Now, once we do that, we have to compare this data for the unknown substance with the diffraction data that is from many substances, many thousands of substances that are available in the powder diffraction file. So, now how we identify that? We look into the PDF and figure out with which card, with which data, the data in which card in the PDF matches pretty well with the data that have been obtained from the unknown material. Say for example, our unknown sample, this shows all these 8 lines, their HKL values, their D values and their relative intensities. And once we start matching this data with the data provided in the thousands of cards that are available in the PDF, we find that these data match pretty well with the data provided for a known copper sample. So, as you can see here, the HKLs all match, the D's they match to a very great extent, and the relative intensities also match to a very great extent. That shows the unknown sample must be pure copper. Now, in this way, whenever we have the X-ray diffraction data has been taken from an unknown sample, then simply by comparing the data in the XRD pattern of the unknown, if we compare it with the data provided in the for the many thousands of substances which are available in the powder diffraction file, it becomes quite easy to figure out what the unknown sample could be.